I would like to start by saying my deep regards to the TFC people. The symposium organizers, my host, Hiriko-san and Bill-san, for inviting me to visit Tohoku University and also to this symposium. So to be honest, I'm relatively new to the field of geoneutrinos, and I'm amazed with the kind of tools it is providing to different scientific fronts. So here, essentially, I will be talking about new technologies, which is geoneutrinos, and here how it is transforming our insights about the global geochemistry. So why, as a geochemist, I should care about geoneutrino flux? So because the answer is straightforward. Geoneutrino fluxes, they has a great potential in understanding the or defining the radiogenic power, and also to constrain the bulk earth composition. So that is why the geochemist should be interested. And these two aspects are also associated with each other because radiogenic power further are further translated to provide information about the uranium and thorium in the terrestrial reservoirs. And uranium, thorium being refractory elements, their elemental proportion are quadratic in quadratic proportions, and that's how all other refractory elements can also be identified by knowing either uranium or thorium. So when we have a better understanding of these two aspects about the Earth, then we can really address several other major questions which is going on in the geosciences. And first of also the very important one is what driving the Earth dynamics. So Earth, like any other planet, was very active throughout its evolution. So in the beginning, there was Earth accretion was happening, and then there was metal silicate differentiation, which lead to the formation of core. Further silicate differentiation for the formation of crust and mantle. And for the present day also, we can see that there is a new crust formation happening along the mid-ocean basalts, and also along the along the convergent boundary, this new formed crust are also subducting. So there is a constant exchange going between crust and mantle, which lead to further heterogeneity in the mantle. So one of the major source of this Earth dynamics, or one of the major driver, is the source, the radiogenic source we have in the terrestrial Earth. So for the current, our understanding about the surface heat flux is pretty much in good shape, which is 46 plus minus 3 terawatt. What we do not understand, what is the contribution of mantle and crust out of it. So that will be a very interesting thing if we can further constrain with a better estimate. And further, geoscientists are also interested in understanding the various structures which we see in the mantle. And that again leads to a lot of controversial ideas about what kind of convection is going on in the mantle, whether it is a whole mantle or a layered mantle convection. And we are looking for some interdisciplinary approach, which geoneutrino essentially provide us, which can provide us information about the radiogenic heat as well as the compositions, so the composition constraint. And then if we are approaching the same problem from two different scientific fronts, and we converge, let's say, at the same conclusion, then that will be great. So to have some idea, and this has already been said number of times, also in the series of talk in this symposium about the thermal evolution, and it will be also said further in the next few talks. So the major source is primordial heat and radiogenic heat, where the primordial is due to the this planetary accretion and core formation. Radiogenic heat is coming from both short-lived and decay of long-lived isotope systems. The first components, this primordial heat and the short-lived isotope decays, they sets the initial condition of the starting of the Earth. However, uranium, thorium, and potassium, they have been decaying throughout the evolution of the Earth. So their estimate in the terrestrial reservoir essentially sets further. They provide useful information regarding how much fuel is left to drive the dynamics of the Earth, or in other words, plate tectonics. So here I am showing a plot. So the plot in the right is essentially based on the some of the assumptions which is shown in the left. So here the Earth is accreting its fraction of mass in time period of, let's say, 5 to 50 million years, and that's how it will all evolve. So, and the plot in the right is being produced for Earth tau age of 10 million years. So the tau age is essentially when about 63% of the Earth mass will be accreted. So here we can see that in the initial around 30 to 40 million years, so only the short-lived isotope decay, not just, there are other contributors, but they are the major contributors, but they decay very fast. And then for the present day, which is this point, about 4.56 billion years, so for the present day, the major contributors are 232 thorium, 235 uranium, 238 uranium, and also 40 potassium. And again, relatively, so this uranium, thorium, and potassium contributes 99% of the total power for the present day. And among them also, relatively, uranium and thorium are contributing the most. So that's why we are interested to understand what is the uranium and thorium content in the Earth. So particle physicists actually putting a lot of endeavor in the last 2 decades, where they have estimated the uranium, thorium in the terrestrial reservoirs, and because a lot has already been taught, said in this in the previous talk, also by Hiroko-san, also yesterday by Greta. So I will very briefly tell you that during the beta decay, there is a production of electron antineutrinos, which are also known as Geo Neutrinos, and only the uranium-238 uranium and 232 thorium decay, they can pass the threshold of 1.8 million electron volt, and that's why they are the only isotopes which are being detected. Only the neutrinos which are associated by the decay of these 2 isotope system will be detected during the Geo Neutrino experiments. So this plot is quite interesting because it's a kind of association of both geoscientists and particle physics people. And this is essentially how we can calculate the antineutrino flux, and they are essentially function of distance. So these are the inputs from the geoscience, which I will be emphasizing here. So the inputs from the geoscience is the most important is the abundance of A, which will be uranium, thorium here, and also the density. And both of these parameters are dependent on the distance from the detector. So here this is the spot where Borexino is placed. So we can see most of the contribution is essentially coming from the near field lithosphere. However, the far field will have the least contribution, and this shaded black zone is essentially telling you that the core doesn't have any contribution in this Geo Neutrino flux. So with that, the fluxes we get through the Geo Neutrino studies, we further convert it and we measure the global present-day thorium and uranium. We have a quite good distribution around the globe of inland underground detectors, and inland they are built underground to avoid any kind of alteration, or you can say to avoid the neutrinos which are coming from the atmosphere, or cosmogenic. So, but here what we can see that there are some of the detectors which has already done their job. They have already counted, like Borexino. Some of them are under operation, like Camland and SNO+. So Indira was yesterday talking about SNO+, and she's very excited to show her results, which I hope will be published very soon. And there are many others which are also under construction and planning stage. And here, just in the last talk, Hiroko-san was also talking about what is the implication of having ocean bottom detectors. So if that will be developed in future, then we will have even better estimate of the mantle heat. So what I want to emphasize here is the Geo Neutrino emissions, the total of their estimate is essentially are three components. Here, just to show lithosphere, mantle, and core, because core does not have any uranium thorium, so it is again just lithosphere and mantle. Lithosphere will have two components, near field lithosphere and far field lithosphere. And in this equation, to again narrow down to our information about the mantle, we really have to just subtract from the total emission the lithosphere part. So here I will be showing the cumulative flux, which is being contributed by these different components. So here this black curve is the total one, and the x-axis is the distance. These are the results from the CAMLand, which was first published by Araki et al. In 2005. So for about 50% of its total flux actually is coming from the nearby 400 to 500 kilometers. And that is also, again, the major contributor is crust. So with that information, there was also a study by Shramik et al., where they have predicted what will be the contribution of these different components of the fluxes. So again, from different studies, like from CAMLand or whatever will be expected from Juno or Boroxino, so it was kind of shown quite clearly that the crust has the major contribution, and that contributes about 50%. The near field crust will contribute about 50% of the total Geo Neutrino flux. So it is really essential to have a better model or a geological model which can give you a good estimate of the near field crust. Here are some numbers which has been produced so far from CAMLand experiments and Boroxino. So the total heat is around 14.6 from CAMLand and is 38.2 from Boroxino. And if we subtract the lithology or the crustal component, then for mantle, these estimates are 10 terawatt for CAMLand and 30 terawatt for Boroxino. So we can very straightforward see what is the large difference in these two values. However, they are saying the same thing about the mantle. So we see a discrepancy in the data of CAMLand and Boroxino. So next I will talk about why is this discrepancy lies. So here is the geological model of Boroxino, which was recently published by Agostini et al. In 2020. So on the right is the surface geology, which has recently been published by Salmon and McDonough in 2022. So Agostini et al. Actually has adopted a model where their near crustal their near crust component was this heat-producing element poor, and also they were carbonate rich. They have also not considered the igneous component in their local geology. And this is what is being revised by Seema and McDonough, and there they have shown a high contribution of potassium magnetism, which we can also see in the plot on the right. Here is the big star is the Boroxino, where the Boroxino is built, and also not just within the 500 kilometer, actually within the 50 kilometer itself, there are volcanic activities. So it is really important to keep in. So it is really important to have a better crustal model for the nearby lithosphere. So this is what being done by Seema and McDonough, and what I would like to here emphasize a little bit about, again emphasizing on how how the geochemical information, which is again the concentration, the nearby lithology, is going to contribute a lot in these Geo Neutrino flux studies. So again, if we see in terms of number, we have the oceanic crust is about 2.7 ppm, and when we go towards the mantle, this values decreasing quite a lot. It is nearly 5 ppb in the depleted mantle. And also, not just the crustal component will have the major contribution, but the upper continental crust will have the major contribution. So that will contribute the most. So it is really important to not just know the nearby crust, but really precisely know the upper crustal composition. So here I'm trying to just make a comparison, which was given by McDonough and Son, where there is a comparison with Agostini model in 2020 with any generic model. So this is a medium Q kind of model, which Hiroko-san was talking about. So here we can clearly see they have estimated, they have adopted a model where their uranium concentration was around 3 times lower than what is expected in any generic model. So here in this cartoon, what we can see that from these two scenarios, if the total flux or the Geo Neutrino emission flux is, let's say, even the same numbers, like 47 TNU for both of the models, and the far field lithosphere is nearly constant for both of the models. So basically there is a balance between how we are going to adopt our near field lithology, and depending on that, what is left will be the contribution from the mantle. So this is what happened with the Borexino model, that they have really underestimated their near field lithology. Because of that, they had a very big estimate for or a large estimate for the mantle. This is also being shown in the figure in the right, that when we have the lithology from the near field is underestimated, then this line, which is essentially hitting the y-axis, and where it cuts will tell you what is the composition or what is the contribution of the mantle. So we can see it is quite high relative to any generic model. So yeah, so at the end I would like to emphasize with these two comparisons that we really should have a very high resolution for our crustal model, and that is really, really needed when we are looking into the fluxes which we are getting from these underground detectors. So there is also an attempt going on regarding revising the geological model of the CAMLand, again by McDonough and Simon. They are revising the near lithology contributions, and their surface sediments are similar to the upper continental crust, which was proposed by Radiogenic and Gao, and their deep crustal model are revised from the study by Simon and McDonough. So after after revising this model for CAMLand, they have, here I would like to show how they are kind of interpreting this Geo Neutrino flux towards by getting into the numbers for uranium and thorium. So here is the estimate from Borexino in TNU, and here it is from CAMLand. So they have actually made a linear fit using these two model studies, two experimental studies, and again, where it hits the y-axis will be the contribution for the mantle. So their Geo Neutrino flux contribution is now 9.2 based on these two experimental revised results, and then in terms of terawatt, it will be 10.2. So when we convert this information of terawatt towards the uranium thorium composition, it is around 13 ppb and around 49 ppb for thorium. Then we do not have potassium contribution so far in this Geo Neutrino flux, because as I said, Geo Neutrino flux will only be able to detect the neutrinos which are coming from decay of uranium 238 and 232 thorium. So here we will adopt some ratio which is quite constrained in the BSc, which is potassium by uranium ratio, and using that, when we include that contribution of potassium also, then this radiogenic power will be again from 10.2, it is now 12.6. So this is just the mantle radiogenic power so far, and when we add the lithosphere also, then it becomes 20.1. terawatt. So now this is the contribution by uranium, thorium, potassium, and it contributes, it is a contribution both from lithosphere and mantle. And this is what the number you see here, the figure in the right. So that's how they go down from geoneutrino flux towards getting information about the uranium, thorium, and potassium in this silicate earth. Okay, so now we will try to again get down into the numbers for uranium, thorium. So from this 10.20.1, which is from both mantle and lithosphere, we subtract the potassium, so now we end up for total radiogenic power. So again, the contribution from both, so it's from the total terrestrial reservoir, which will be a number of, this will be around 16.3 terawatt. And from where there, if we estimate, change it to the convert it into the uranium thorium concentrations, it is 20.5 and around 77 ppb thorium. So this is, when it is compared with the previous studies, it is similar to what is being proposed by McDonough and Son for the periodicites. And when it is compared with the CI carbonaceous chondrites, so then it tells you that the silicate earth is about 2.7 times of CI chondrites. So now we are getting from uranium, the geoneutrino flux towards getting a compositional model for the earth. So why it is important to understand the bulk earth composition? So it is important because we want to know the nature of accretion of material in the nebula, and then when we also add information for other planets, then we can have a better model for the planet formation. Further, we can also understand the solar system planets, and then going to the big questions like discovering life elsewhere, which was also talked by in the last talk by John about how Earth and life are correlated and all. So that's why we are really emphasizing into understanding the bulk Earth composition. So before going into the compositional model of the Earth, let's have some look for the numbers we have for different elements, which comprises the terrestrial part of the Earth. So here, in terms of atom percent, oxygen, we can see that it comprises about 50% of the total Earth. So 1 out of every 2 atoms in Earth is oxygen. In terms of weight percent, we can see that the first 4 elements, they are comprising about 30% of the Earth mass. And if we also include the other 4 elements, which are the next competitors, then together they are comprising the 99% of the Earth mass. So that's why we are interested in these 8 elements. And further, from geochemistry point of view, calcium will be playing a very important role in understanding the uranium and thorium, and that we will see further while. And because they are refractory, they are calcium, uranium, thorium, they're all refractory. If we know uranium or thorium, we can again calculate calcium, estimate calcium, and further all other 32 refractory elements. And then we can have a better model for the Earth composition. So this compositional model are seismically also defined. So here the figure in the right shows how seismic wave velocity changes and defines different layers within the Earth. And they are essentially they are in correlation with the change of the mineral phases within from upper mantle towards the base of the mantle. So here in the upper mantle there is olivine, then pyroxene and garnet at this transition zone between upper mantle and lower mantle. Olivine actually encounters a phase change where it changes into vasillite, ringwoodite, meserite. And in the lower mantle, again, which is not very well constrained, there are different proportions of bridgemanite, ferropericlase, and calcium perovskites. So this we can actually better see by this figure in the right. And here the x-axis on the top is the model proportions of different minerals. X-axis below is the temperature. Okay. The pressure here we can see with depth is increasing, and okay, so I will just focus on this part that the first 150 kilometer is very well known, that we know this. It is a different proportion of olivine comprises about 60% of the total mineralogy, and then we have clinopyroxene and OPX. With depth, clinopyroxene and orthopyroxene again changes into garnet. The sharp seismic changes actually tells you more about how there is transition going on from one mineral to another. And the more important part here to focus is the different, three minerals which are not very precisely known so far, what is their proportion in the lower part of the mantle. And then we go to the models which we know from different studies. There is one end is McDonough-Sun pyrolytic model, other end member is Chavoy model. So the Chavoy model is predicting enstatite chondrite kind of composition. So what we can see here is that we have different proportions of these three minerals in the lower mantle, depending on which model we are going to adopt. So, for example, the first McDonough-Sun and Turcotte-Sibbert, we can see the content of calcium is going to be twice, and accordingly, accordingly the Turcotte-Sibbert models, they are high Q models. However, McDonough-Sun, it's a medium Q model. So here also, I will just quickly go in these numbers. So magically, how you can see here for low Q to high Q, this uranium is concentration in the BSC is very similar to what we see in terms of powers. So this is 10, 20, 30 for low to high, and similarly you have uranium concentrations from 11, 20, and 30. So this is where the various models lies. And we have independent constraint from Geo Neutrinos, so which is telling a radiogenic power of around 20. And when we compare it with the CI chondrite composition, these are the ratios which it will have relative to the chondrites, depending on which model you adopt. Then what we can observe here is that from two different perspectives, we have a common observation that both from the medium Q model and the Geo Neutrinos, we see that 2.7 times of enrichment in the bulk-silicate earth composition. So that's a remarkable observation, and you can say it's now we are approaching towards a better model for Earth. So just very quickly, we have already seen a lot about the compositional models or the heterogeneity within the mantle. So there are different thermal and chemical domains within the Earth, and they are seismically also being identified, and LSVP and ULVZ are really focus of the present day, and they are subducting along the subducting trenches. They are not just subducting in some layers, but they are going deep down into the mantle, and that initiates the whole discussion about the hole versus layer mantle convection. So the one more important question here is, can Geo Neutrino help us to identify this kind of mantle heterogeneity, which was also shown by Hiroko-san, but here I want to emphasize a little bit more that yes, there was a study by Stramik et al. In 2013, and they had this kind of assumption to produce this mantle Geo Neutrino flux, which is stating the uranium and thorium in the mantle, and they are able to successfully show these two anomalous zones, which we know under the Pacific and the African plate. So definitely it is going to be of a great help. And yes, so the whole discussion about the understanding the local lithosphere is actually can be avoided or not avoided, but it would be very good if we have ocean bottom detectors, which was again very nicely been put forward by Hiroko-san. And what I just very quickly want to show about the figure in the right, that the Hano project, which was the ocean bottom detector project, it kind of showed that the major contribution was coming from the mantle, which was in the previous, for the inland detectors, we saw that the major contribution was coming from the local lithology. So we really needed to know the near field crust quite well. So we come to this slide, what was the motivation of me going going for this Geo Neutrino studies. So it defines the power of the Earth, but then it is proportional to the, we need to really have a better constraint on the geological assessment of the nearby crust. The constraint of the bulk Earth, Geo Neutrino can also provide constraint on the bulk Earth composition, and this time it is independent of any kind of Earth structure. I would like to leave you with this slide, like we have which is also known as the concept of anekantavada, which is in Sanskrit, no one-sidedness, none one-sidedness. So there are several point of views. No single point of view comprises the complete truth. So these views are not wrong, but merely incomplete. So when we have an interdisciplinary approach like this symposium, where people are thinking about some common, they are approaching the same problem from different scientific fronts, then it will be really great if we come to some common conclusion. So with that, thank you so much.